Okay, always one more step with this new computer. I got that button that says join with audio. All right, so we're going to be talking about cubics here. I'm going to be talking about cubics. And for me, it's the richest algorithm of study that we have. I think there's more good things that come out of it in terms of mathematical principles than any other function. It's simple enough to understand, but complicated enough to push us forward in our understanding of the geometric, numeric, analytic, and graphical principles that we are going to talk about until May 15th. Identifying point of inflection. Shouldn't take long to learn how to do that. Piece of cake. Rate of change, point of inflection. A simple memorization takes care of that. Finding the max and min, should they exist? It's got a little weight to it as to where that, how we can find those numbers without calculus. And we're going to do everything without calculus. Although the foundation upon which I'm going to do what I'm about to do is certainly leading us towards differentiation and integration, without a doubt. And students struggle mightily with really understanding those on a conceptual level. The mechanics aren't too bad, but the understanding conceptually, yeah, it takes some time, it takes some processing. And I really think that thinking about some of those early foundational principles, thinking about them before you get there is so important. So that when you get there, you got a chance to understand what you're looking at. And so we're going to be moving into that territory with this particular problem. But on tests, point of inflection, you should want that asked. Rate of change at point of inflection, you should want that asked. And this is pure memorization too, from just a symbolic perspective. All right, so deep, beautiful algorithm that we're going to be studying. And here are some videos that will help push you towards that understanding. What we're doing is really based on completing the cube. And I don't think you're going to see that out there in internet land. So look at this and you'll get a chance to see the geometry behind this stuff. Putting cubics in graphic form. Last problem I do on this video, I'll just do that quickly for you so we can see what cubics look like. Geometric integration, again, well, this is calculus. And so if you want to see how it is after you do some of these problems for a while, and then go here, I strongly encourage it. I really think you got to start thinking about those issues before you get to a calculus class. And then I did a geometry of change with a class one time and did about 8 or 9 lectures. And then stopped because I thought I was losing the students other than the top 2 or 3 kids who were paying critical attention to what I was talking about. Other folks really weren't. So, but you might want to look at some of those. All right, let's have at it. Let's look at a cubic, a negative cubic, negative dimension. Hard to describe it geometrically when we're talking about negative length. But -3 times -3 times -3 is -27. Lots of zeros at the end there. And a smaller number is actually -3.001. Bigger magnitude, but it's a smaller number. So as I move from -3.001 to -3, the magnitude of the size of the cube is getting smaller, but the numbers are actually getting bigger. Okay, they're very awkward. But I didn't do this on a calculator. I hope I have the pattern. Usually make a mistake somewhere talking to you and then doing calculations quickly. Often just butcher something, but I'm pretty sure this is correct. And if we look at the change in dimension and the change in the volume, call it that, we get a 0.027 to 0.001 volume to dimension, rate of change of 27 to 1. So this cubic is increasing at x equals -3. The graph is going up. There, I said it more easily. The graph's going up. And a -2 by -2 by -2, if you want to freeze frame this and look at the numbers and try to figure out what the pattern is and why, I'm going to show you the pattern a little bit later as to why as well. But it's going up at 12 to 1. So this is going up as I move left to right, increasing, but less quickly. Less quickly. So I'm going up, but less quickly. And if I do -1, -1, times -1, if I change the dimension by 0.001, then the change is here. Can I put some zeros in here? Right, 3 zeros cubed is 9 zeros. And so here's the change. Okay, still positive change, 0.003 divided by 0.001. I mean, I think I can ignore this. It's significantly smaller than this amount of change. So looks like I'm going up 3 to 1. And when I go to 0, I can't draw 0 times 0 times 0, so there's no volume. And really, there's no change. It's flat. So what we've done is we're increasing less quickly, and then we're flat. That's what we've done thus far. Except that we haven't looked at the numbers in between it all. So we've just looked at 3 locations, 4, excuse me, going up at 27 to 1, boom, at that instant, going up at 12 to 1, that instant, 3 to 1 at that instant, and then flat, no change. Now let's examine the, okay, so I guess I'd already done that here, anticipating this discussion. Okay, and then if we look at the entire cubic, y equals x cubed, maybe it makes a little more sense here. Right? With each conversation, we'll hopefully have a point of reference that's a little further along the conceptual ladder until we get a deeper and deeper understanding. So I decided to do a 2 by 2 by 2. I didn't draw it this time. And then I went to 2.001, and I do believe that we get that 12 to 1 change. So at 2, I might be going up at 12, -2, I going up at 12 to 1, and +2. Well, it doesn't look like I hit the same place, but right at that instant, I'm going up at the same rates. All right, so what's going on geometrically? Let me get my high tech. Let's turn it this way. My high tech manipulatives here. All right, so what I have here is a cubic. There, let's see. All right, hiding the open part so you can see a box. All right, and let's pretend that this box, it's a little dark here. Let's see if I can get this lighten up. This, so I'll put it, I have a very strange computer right now. It's changing the darkness and lightness on the screen. But anyway, hopefully you've got something that you can see well. So that's a 2 by 2 by 2 cube, 8 units of volume. And if I increase the dimension, it's really the thickness of what layer I'm going to put on it. So I'm increasing the height when I do this by that little amount, which I'm referring to as, I guess I got to come over here, as 0.001. That's the thickness of the cardboard here, 0.001. And so this has 8 units of volume, and when I slap this on there, I've just put a little more volume on the box. How much volume have I put on the box? Right after this decimal place. All right, that's actually what I've done. And if I kept slotting more and more layers, I'd eventually have a 3 by 3 by 3 box, something the size of the room, just keeps going up faster and faster and faster because each layer is a little bit bigger than the previous one. Okay. So, what else do I want to say? All right, so we have this decreasing rate and then increasing rate, and that right there is what is called the point of inflection. And maybe I can make a fool of myself here and go, whoa. I hope the choral folks can tell me if that's a point of inflection at the top of my voice. Whoa. I don't know. Maybe that's a silly thing to say. But this is kind of a deceleration, acceleration. All right, and these values, 12 to 1, you can think of them as velocities. Yeah, and the cubic tells you where grandma is. So at 2 o'clock, she's 8 miles north of the Vermont Mass border, heading due north. And she's traveling at 12 miles an hour. And we could tell you how she's accelerating too. But this is going into the calculus, right? But I really haven't done anything here other than crunch some numbers and look at them, make some connections, geometric, numeric, graphical, and now analytical. Let's take a look at a cubic. Let's look at some of this change. Up, turn the cart the wrong way. Let's spin it around, get you dizzy. And let's look at a cubic. All right. All right, let's see if we can get everything on the board centered. Move it back a little bit. There we go. Yep, it's been a long day already. Yeah. All right, so back to my high-tech manipulative. So if the rate of change at an instant is really about a layering process. Not exactly that, but it's good enough. This layering process, when will I not be going up at all? When there's no box. If there's no box, you're not putting a layer of change on it. And you might as well look at the layer of change and study it a little bit more. Here's a layer of change. And slip it on the box, right? Well, if you notice, there's a shape here staring at you. It's a square. There's another square. There's another square. How many squares do you see? I see 3. And what's the dimension? 2 by 2. And 2 times 2 is 4. And 4 is 8. And 4 is 12. Whoa. So what do I have here? Back to, back to the 2 by 2 by 2. Should have done this over here. I'm not making this again. All right, so 2 by 2 by 2. Whoa, 12 units of change. And what was the 3 by 3 by 3, even on the negative side of things? Where's my 3 by 3 by 3? Oh, so if this was 3 and 3, well, that would be 9. And another 9 and another 9. 3 9s. Oh, 27 is appearing. There's no action in here. It's what the numbers are saying. All right, so when we don't have a box, there's not much change. So let's go to 0 here. Here's a box, 0, 0 to 0.01. I had to keep the decimal small because 2 decimal places means cubing. I got 6. 1, 2, 3, 4, 5, 6. Not much change in this column. And when there's no square, oh, I haven't looked at the square. Well, I got some numbers up here, crunching. If I square 3.0, 4 decimals gets me 8 decimal places. And it turns out that the change is 6 to 1. So when I'm at 3, I get 9 units of area, and I'm going up at 6 to 1. And what's the geometry behind that? It's the same thing. It's a layer of area on that. There's the layer of area. It's got a length of 3 and a length of 3, and a 0.01 is a width, and a 0.01 is a width. Well, there's your 0.06 accumulation. I'll have to draw it bigger so you can see it. And there's your error. And we can eliminate the error by putting more and more zeros in. And that's really about limits. But back to the geometry. No box, no change. No box, right? No box. Boom, 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 boom. Then when I draw that layer of area, still got 0.01 as a change in dimension, but no length to it. All right, so it's got some width, same width, standardized, but there's no width. There's not much change. But a linear 0.01, this is significant change compared to what's over here. And if you're seeing this column change, please write to me. I'll make sure we can get you some, well, just write to me, I'll write back. So the change is really here, which means if you want to graph a cubic, you might consider going from local behavior to end behavior. So locally, I'm at 0, negative 18. I know I'm going down at 6 to 1, but I also know that this critter is coming back up eventually. So I know I've got something. Well, I put that in a bad spot. 0, negative 18. I know I've got something that's going to look like that. The question is, where's the point of inflection? Okay, we're getting there. Yeah, point of inflection. Minus b over a tells you where a linear function changes from positive to negative or vice versa. Negative for the most part. We do have some flat lines, but for the most part, it's where it changes sign on the x-axis. Minus b over 2a is the average of the roots, right? Take the roots, something that produces a 0, or any constant, really. That's what minus b over 2a tells us the most significant place on the quadratic, and minus b over 3, again, is the average of the roots. This is what's going to get you the root of a linear. This is going to get you the vertex of a quadratic, and this is going to get us the x value of the point of inflection where acceleration changes. Yeah. So let's actually do one. Point of inflection, minus b over 3a. Minus b, minus 3 over 3 times 1 is 3. Do I want to make this negative so that it's easier for you to see? Yeah. Let's make that negative. So that makes this positive, which makes our x equal to 1, which is easier to work with. All right, so right now, I know I have 1 times, this is the a term. You just take it like you do the quadratic. That's a 1. I'll change it on the last problem. X minus 1 cubed, very similar to what you do with a quadratic. I've got a linear component, x minus 1. I guess I should have told you that a x minus h cubed plus m x minus h plus k is the graphing form for cubic. And so we need m, we need the slope at the point of inflection, and we need k. Well, k is easiest to figure out because you just drop 1 into the function. And then we get rid of that now. If I put a 1 in, I get 1. It's all about the coefficients. All right, so that's what I get. And I get minus 9, minus 27. 1 minus 27 is minus 26. Oh, I'm sorry, that was k. Minus 26. And now I've got to find the rate of change. And the rate of change, I'll use m for slope, is a multiplier. And you can find it by c minus 3a h squared. And h is that value, minus b over 3a. So it's not that bad. We're given c, minus 6, minus 3. We know a is 1. All you got to do is square that. And so what I have is minus 9. So I now have the need for an eraser. So I'll get one. All right, so I'm throwing a lot at you here. You're not expected to know this the first time you hear it. I'm just planting some seeds. We're going to talk about it every day a little bit. Every day a little bit. So now I can visualize 1, negative 26. So 1, negative 26 is the point of inflection. I know I'm going down at 9 to 1. So I've got something that looks like that. I might as well find my y-intercept. We've been doing that all term with all kinds of functions, so I hope you know. It's negative 18 in this context, put a 0 in. Negative 18 is above, so 0, negative 18. Right? And if I want to find the x values of my maxes and mins, well, I suppose if I want to know if this has 3 real roots, I've got to figure out if this is above 0 or not. So I think I'll do it. So m is from, oh, I've already got it. M. So, x values. So x is h plus or minus the square root of minus m over 3a. Yes, there's some memorization. Will I hold you accountable for that? Probably not, but let's look at it anyway. So that's 9 divided by 3, so that's the square root of 3. And this is 1 minus the square root of 3. Right? H is minus b over 3a, the point of inflection. Where I go from concave down, we call that a concave down shape. This is a concave up shape. Okay, so we change concavity. And honestly, this is not too bad because we know the square root of 3 is 1.73. So roughly, this is negative 0.73 is going to get me a y value. And that is a local max. I mean, there are bigger numbers in this function, but very important. And therefore, 2.731 plus the square root of 3 gets us this x value, which is what was it, 2.73. I've done all of that without calculus. I wish I could show you where I got that algebraically. I did it in the 90s. Then I did it with a Maple program, Canadian tech company. They kept changing their iterations of their software. They lost me in their tracks. So none of my stuff was compatible with all their changes. All went out the window. And I can't remember what I did. I wasn't doing calculus at that point. So I don't know. But I can see from a calculus standpoint why it works, and we'll have those discussions for some of you. All right, so what do we do? One more time. We're trying to find points of inflection, the x value first. We find the coordinate of the point of inflection by putting that x value into the equation, which is no different than what we did for graphing form for the quadratic. Rate of change at the point of inflection, that's actually enhancing our conversations, looking at what goes into that geometrically, numerically, and otherwise. So let's actually do it here with, let's put it in graphing form. So what do I know? I'll just do one real quick. 2x, I know I got a cubic, I know I got an x, and I got to figure out what number completing the cube is based on. And if you want to see that geometrically, you're going to have to look at that video. So minus b, 18, the opposite of this, divided by 3 times that is 6. So I got a 3. X minus 3, x minus 3. I got to run a 3 through here. And this is fun, actually, because in a quadratic, we have a 2-to-1 ratio. In a cubic, we got a 3-to-1 ratio. So I'll just get this number 54. If I multiply that by 3, I get 162, and it'll be the opposite. Because there's a 3-to-1 ratio, which means when I add them together, I get twice this, minus 108. Right, and so I still have to put 3 in here, so that's minus 30, and plus 5. Minus 138 plus 5 is minus 133. All right, so 3 gets me minus, where can I show this? I don't know the rate of change there yet. So point of inflection. 3 gets me minus 133 is what I thought I said. And I hope I'm not making any, I'm doing this on the fly. What I'm doing works. If I make a careless error here mathematically, then you check it, obviously you're going to find a mistake. Maybe we'll throw a 0 through and see if we get 5 at the end. All right, so now I know that this number is minus 133. And now I need the slope at that instant, which comes from c minus 3a h squared. C is minus 10. Minus 3, a was 2, and h was 3, so that makes that 9. And so I've got minus 64. So minus 64, it's going down pretty steeply, I think, which means that our graph is going to look like this. And there's your point of inflection, minus positive 3, comma, minus 133. And I'm going down at 64 to 1 at that instant. So I guess I'd have to find that x value to find out where my y-intercept is. My y-intercept is going down at 10 to 1. So I do know it's going down. So my y-intercept is probably about here, 0.5. I got a lot of information here. You know, I can easily find this value too. If I have there's symmetry here around the point of inflection. Okay, and let's throw a 0 in here and see if we get 5 out when I put minus 64 in. So 0, cube, minus 27, minus 54. 0 plus 192, I believe. Minus times a minus, plus 192 minus 133. God, I hope that comes out to be 5. So let's put 54 with that, 54 with that, 87. All right, 192 minus 187, 5, yes. All right, I guess I didn't make any mistakes. All right, that's a mouthful. There's a lot to look at, especially the interplay of all of these graphs. Let me do that. That's the last thing I want you to see on this video.
2x cubed, going up twice as fast as x cubed, minus 18x squared, cup shape down, minus 10x, linear function down, plus 5. Okay? Your brain's supposed to add all those graphs, all those y values and all the rates of change at those instances in order to get this. Why is this easier to see? All right, let's take a look. Add. Okay. Add. The point of inflection. I have a cubic. That's flat. No box when I put 3 in, right? There's no volume. It's not changing. It's flat. We talked about that earlier. Minus 64. Right? And this is just a constant. So it's really the interplay of these two graphs. And if this is flat and that's going down, then locally, we get something that looks like this. Okay? It takes on the rate of change of this linear component at that instant. And then when this is pulling up at 64 to 1, and this is pulling down at 64 to 1, the rate of change is flat. That's what's causing those local maxes and mins. Very long, lengthy lecture on one problem. All right, but finding the point of inflection, the rate of change at the point of inflection, memorizing a little bit will get us 2 quick problems that'll probably take 30 seconds for each one. Once we talk about it for a while, once we practice it for a while, and then we can continue to talk about it a little more deeply, and we'll get some good conversations going, hopefully. And for some of you, might not be looking at this too much. Still got too many problems from the first half of the semester that you still got to look at. No gaps. Whatever you got wrong, it's coming your way the rest of the year. And I think that'll do it for now. All right. Toodaloo.